or decent lunch. So yeah, next session is about the power of indexing. I think last 2 days, each and every session, people are talking like should create an index to get the performance benefit. But there is a bigger question in mind, like which index I should choose, and how all the available index type in the Postgres SQL. This session is going to cover that part. This is going to present by one of the very known face in the community, Pavan. Pavan is working on a Postgres since 2006, and right now he works at second quarter. So yeah, welcome, Pavan.
Hello, everyone. So the topic of this session is power of indexing. Looking at the turnaround, it seems that you are not yet tired of, after 1.5 days of constant technical bombarding. So I'll try to keep it, I'm try to not go into too much internals, but if there are any questions, please feel free to ask. So something about myself, I've been contributing to Postgres for almost last 12 years now. 2006 is when I got introduced to Postgres, and since then, that's the only thing I've been doing in different capacities and different roles. I'm the primary developer, committer, and maintainer of the Postgres Excel project as well, which is a shared nothing, distributed, scalable clustering solution forked out of PostgreSQL. So it's not, like time series where time scale where you have core Postgres and extension. It's a fork of Postgres, but still pretty close to the vanilla Postgres. I'm also part of the team which is organizing this event for last few years now. We started in 2013, the small meetup in Pune, and now it has grown into a full-fledged conference with support from all of you. Currently, I work for Second Quadrant. I've been working there for the last 3 years, though many of my colleagues there, I know them for many years now. And before that, I was at Veritas, Symantec, and Enterprise TP. A brief about Second Quadrant itself. That's the company I work for. We are one of the major contributors to PostgreSQL project. We have contributed several patches, several big features, and some of those are listed here. You might have seen this in other slides as well. So what this talk is all about, in what we are going to see is what are the different mechanisms by which you can access data in PostgreSQL, and with focus mostly on indexes, because that's what we all like. But before talking about indexes, let's first look at the heap, the place where the data, the actual data is stored, the primary data is stored. Whenever you create a table and insert rows into that table, what happens underneath is there are file system level files that get created, and each file is made up of X number of blocks, where the number of blocks would vary depending on what block size you have chosen. But typically, each segment is 1 GB in size, and typical block sizes are 8192 bytes. So you can sort of see that the heap is made of a series of blocks, starting with block number 0 and going forward. Each row that gets inserted in the heap is assigned what we call TID. It's a physical identifier, location identifier for any row in the table. It's not a permanent identifier, because if you update a row, its TID may change. But at the given point, for the given version of a row, TID is the physical location, and it's primarily made up of two parts. There's a block number and there is an offset. Block number is clearly the block you know, a number in the file. And when I say file, I don't mean 1 GB file. You know, if you have a terabyte relation, you know, the block could be referring to you know, some block in you know, file number n. The offset, on the other hand, is a you know, sort of indirection within the page. So in every page, and I haven't shown it here, but in every heap page, what you have is set of you know, line pointers, what we call line pointers. And what you get is, you know, from the external world that we'll see soon, you refer to tuple as, or a row as, of block number offset, but within the block, because tuples can be of variable size, internally we'll have an indirection where we'll say, okay, tuple at offset 1 actually starts at byte 27 and goes up to, you know, say byte 100. So that sort of indirection happens within the heap block. When you initially insert data into the table, you know, it will, and I'm being simplistic here, but you know, the data would get stored in a sequential manner, right? So you know, first 100 rows would probably go to block 0, the next 100 rows would go to block 1, and so on. But that you know, ordering is not maintained, because as you update tuples, when you delete rows, as the you know, space gets freed up in heap blocks, that can be reused for tuples that are inserted later. So unless your table is a append only table where the only operation that you do on table is, you know, appending new data, most likely you know, even if you started with a fully sorted table, sooner or later, you know, your table data would have been mixed up. So how do you access data in the heap? And the most primitive access method in PostGIS is a sequential scan. And as the name suggests, what you do is you sequentially go through each block, and depending on what you are looking for, you'll return one or more rows. For example, in this query, if I'm looking, you know, in a table EMP, if I'm looking for, you know, all employees with city name Nagpur, since I don't have anything else right now on the table, my option is to go through the block 0 to block n, assuming n is in the last block in the relation, and look at every row in that table, and look for if the row has value for the given column, or the column that you are searching for as Nagpur. Well, that's not, you know, not necessarily a bad way, especially if your table is small. But you know, it can get trickier if your table size increases. As I said, you know, sequential scans are not always bad. There are two prime advantages of sequential scans. One is, as most of us know, that reading sequentially from a disk is always much faster than doing random access, right? And this is probably, you know, has become less true with SSDs, but it's still true. I mean, even if when we do experiments, we still see that you know, sequential access on SSDs are also faster than you know, random access. And one reason is because kernel can also do a lot of optimization when it sees a sequential scan coming on a file. So you know, if you have read block 0 to 10, it sort of imagines that you will probably read, you know, next 5 blocks as well. So it will read ahead those blocks in kernel cache. So that's why at the application level or at the database engine level, sequential access, sequential reads are quicker. So yeah, I mean, you know, sequential access works fine if your data is small, you know, or basically, you know, if you are going to anyways read most of the data. You know, you want to do a count star from a table. I mean, unless you read through all blocks in the table, there is no way you can definitely you know, answer that query. So you know, if you are anyways going to read everything from the table, just read sequentially. Don't worry about, you know, having any index on that table. Nothing is going to help if you are, you know, going to read everything. But what if you are looking for a very specific row in a very large table? A table with millions of blocks is not uncommon for none of us here. So if you are obviously I'm trying to just squeeze in more data in the heap to show that there are a lot more data here. There are still just few, but what we are trying to show is if your table is very large and if you are looking for one city, Kanpur somewhere, if you are going to do sequential scan always to go to that row, it's not going to be very efficient. And that's when what the solution that we all know of is building index on table. And what is an index? I would say that an index is a secondary table, at least because in Postgres the structure of index, or at least the the lower level structure of index is no different than a table. So index is a secondary table which maintains and stores information about the underlying table on which you have built index. Now, unlike the underlying index, underlying table, the index will have certain properties which are maintained all the time, depending on what kind of index you are choosing. I think most of us must have seen index printed on our college textbooks, where you'd say if you are looking for, so you got a technical book which is like a 600 pages long, and let's say you are looking for a specific topic within that book. Now how do you really find let's say I want to, for example, I want to know about indexes in a book which talks about relational database systems. How do I find that information out? So the last page on the last few pages of a book would have that index where you say, this particular term appears in these many pages, and then you can basically go and look up those pages individually. Very similar to that, the index in a database system would hold the key and the pointer here is nothing but the TID that we talked about. Again, it's not true for all index types, but for now I think we'll assume that that's what the basic index structure looks like. So having talked about why index is important and what it does at a very high level, let's look at what are the index types that Postgres supports. And this is not extensive list of index types. I think someone was mentioning that Postgres, I think Sunil from Microsoft mentioning that Postgres is an extensible language. So by design we support methods by which you can extend capabilities, add new index types to the system. But primarily I would say these are the 5 different index types which you will encounter pretty often. Btree indexes, hash indexes, Brin, which is I think it's new in probably 9.5, and Gin and Gist indexes. So let's what I'm going to do is spend some time looking at Btree indexes in more detail, because to be honest, that's probably the most widely used index type in Postgres, or for that matter I think any relational database system. That's also the default index type in Postgres. So a Btree index, it satisfies certain properties. Any Btree index, irrespective of which data type you are using, every Btree index would have certain properties. The tuples in the index would always be sorted by some order, and most often that order is the key on which, or the column on which you are building the index, whether it's a single column index or a multi-column index. There is always an ordering which is defined between any given 2 values of that particular one column or multi-column, and that comparison would always return the same value irrespective of how many times you compare them. So that ordering would be guaranteed in a Btree index. That ordering could be reverse, it could be ascending, descending, but the ordering would be guaranteed. Then the every tuple in the index would have the key and pointer to the heap. So I think that's pretty clear that so the column value on which you have the column on which you have built index, its value, and the actual tuple location in the heap. That's what the Btree index would store. Another property of Btree index is it's always a balanced tree. So the depth of any leaf node in the tree always remains same. So irrespective of which key you are looking for, the access time is constant. It can be less or more depending on how large the data is, but the retrieval time is constant because the depth of the tree is same for every branch. And it's also the default index type in PostgreSQL. So if you don't do anything special, if you say create index on this particular table, on this particular column, it will always use Btree index by default. So let's look at a few examples. Let's start with a simple case where I have a EMP table, the same table that we had earlier, and we don't have any indexes on the table. You are doing a query which says select count star from EMP. It's anyways going to read all blocks on the table. So it will do a sequential scan. The planner would basically prefer a sequential scan. Even if there was an index which was available on this particular table, we would have still ended up doing a sequential scan. Even if even if you do a point query, so the first was a aggregate query where, as I said, you need to read through all the blocks anyways. But the second is, let's say that ID column is unique in this table. Even in that case, only one row is going to be returned. It will still do a sequential scan because there is nothing else to offer here, right? I mean, planner doesn't see anything, and it will always sort of default to sequential scan for accessing any table in the system. What if we build index on this table now, right? So let's build an index on column city and build a unique index on column ID. ID is unique in the table, whereas city obviously can be duplicate. If we go back to our query and sort of rerun the queries where in the first query now we are looking for city equals to Nagpur. Now remember we just built an index on this table, and someone might say what happened, I thought I built an index, but it's not, the planner is still not referencing any clues why it's not using the index. Not really, because planner doesn't really know that how many blocks are cached. It has some idea, but that's not the main reason. Exactly right. So what we are missing is we built an index, but we didn't update the planner's information about the statistics. So as soon as you do, if you do analyze on the EMP table, and what it does is basically it collects sample rows from the table and would build the planner statistics, so that planner has better idea about what are the columns on which there are less duplicates or no duplicates, or if there are any columns where only certain values appear more frequently. So that information later allows planner to basically plan a query in the right way. Obviously planner would also look at how many blocks are there in the table, how many rows are there in the table, whether the table has been vacuumed, not vacuumed. It looks at a bunch of stats, and these stats basically come from different mechanisms, but it needs those stats to make those intelligent decisions about planning. So once we analyze, and then we run the query, that's pretty awesome. I don't know, maybe I probably, yeah, it probably, no, I think I'm right. Why it's still using sequential scan on the table is that the table is pretty small. It has just 100 rows in it, and even if you have built an index on top of that, you analyze the table correctly, it will still use sequential scan because it thinks scanning one block of table is cheaper than going via an index path, even when you are just selecting one row in the table on which you have an index. And we will see why that happens, why indexes on very small tables can, planner may not still prefer those paths. So that, let's do that now. Now what we are doing is we are inserting a lot more rows in the table, and again reanalyzing the table, so that planner now knows that instead of 100 rows, now there are 10,000 rows, and this is the sort of distribution of values in the table. Now if I rerun the query, the first, which is the point query where I'm looking for ID equals to 2, now planner knows ID is a unique column in the index, and if someone is looking for ID equals to 2, it's only going to get one row. So if there are 10,000 rows in the table, which means if you remember, if you recall, I deliberately added pretty large columns in the table, so there are a lot more blocks, underlying blocks. So planner would say it's worthwhile to go via the index path and fetch that row instead of scanning through 100 blocks of the table. The second case is sort of it's curious again. Now here in the same table there is an index on column city as well, and we are again looking for one particular value for city, but instead of doing an index scan, the planner chooses a bitmap index scan, and then does a bitmap heap scan with recheck condition. And I would like to spend a minute on explaining why this happens. Now if you look at the way the table is structured, the city column is not a unique column in the table. So there are many duplicates for that particular column value. There are only 25 cities that we have inserted in the table. So every city has 400 duplicate values. Now what planner is thinking that if there are 400 different 400 duplicate values, and if I do index scan, even though it can find those 400 index tuples quite quickly, when it comes to fetching that data from heap, now remember that access is going to be a random access, because even though index is sorted, the heap probably is not, and definitely not in this case. So if we do an index scan, what would happen is it will lead to 400 random reads from the underlying disk, which is not preferred. Instead, what we do is what we call bitmap index scan. So in this case, the executor would go through the index, will find out all the underlying blocks from the heap where this value exists. It won't read, but it will just collect that information, that okay, block number 0 has city Nagpur, block number 10 has, block number 20 has, and it will collect that information as a bitmap. So there is a 1 bit for every block in the table, and it will collect that information. And later on it will basically sort that TIDs by their block number and then do a sequential scan. I mean, not do sequential scan, but basically read those blocks in a sequential order instead of doing a random read. So you'll still read 400 blocks, but this time you'll read them in a sequential fashion. Any questions there? I mean, again, as I said, this data is sort of synthetic, so you may, in your minds, might think that the way the data has been inserted in the table probably even if you had done a index scan, you might have done actually a sequential read. But in real world, that's not how, and the planner doesn't have that knowledge. So depending on how many duplicates are there, what kind of, how many rows it's going to read, planner chooses between either an index scan or a bitmap scan. Yeah. Mm-hmm. Right. Yes, order by would have impacted the because then you can't really go by bitmap because you have to sort of honor what the index is telling you about the ordering. So I think I have a slide where it says that for order by clauses, index access is preferred. So let's look at some of the internal details about B-trees. So B-trees are sort of made up of leaf nodes, and there are internal nodes. So in this case, this is the this is the indexes leaf page, and those values are basically block number offsets that we talked about. So the index is sorted by the column on which you have built it, whereas the TIDs can point anywhere in the heap. All the leaf pages, and for that matter all the alternate pages, are always linked by previous and next pointers in the index. The index does not contain any visibility information. I'm not going to go into details of that. But basically, what tuples in the heap are visible or not, that decision is made by the information that's stored in the heap. Sorry. So this is how at the very lowest level the heap, the Btree index would look like. You have an index leaf page, which is pointing to the actual heap where the rest of the data is stored. The index would only store the column value on which you have built it. As I said, all Btree leaf pages, they are always linked by the previous and next pointer. I don't know if the arrows are like really visible, but what I'm trying to show here is, the index, if you look at, it's all sorted. So you start with A, ends at V, and these blocks are chained together so that you can go from one block to other block without restarting from the top of the index tree. This is, we are going one level up. So in the previous slide, or this slide, we just talked about the lowest level of the tree where there is an index leaf page and which is pointing to the heap pages. But if you go one level up, because your index itself could be pretty large, so what we do is we build another level of index on top of the leaf pages. So now the non-leaf page will tell you how to reach to the index leaf page, but it doesn't basically, from here you cannot go directly to the heap, but you can basically reach to the correct heap, to the leaf page. And this is more complete picture, where you have now another level of sort of internal non-leaf pages. And then there is a meta page. So this is a complete picture of an index where you have a meta page which points to the root page, which then points to the actual leaf pages, which then in turn points to the heap pages. Now if you look at, if you have to do an index scan with this structure, you'll have to do at least 4 different block reads every time, assuming that obviously you can sort of argue that these blocks would be cached, but you still need to go through all of them. You need to search within those blocks to find the right pointers. So even if you are not spending on disk reads, you will still need to process information stored in those internal pages. And that's why when the tables are very small, it's cheaper to do in sequential scans than than going, via the index path. You would notice that even the internal heap pages, they are always linked by previous and next pointers. So that if you are looking for, Surat, you don't have to like scan through all the leaf pages. You can basically follow the next pointer within the non-leaf pages and reach to the right node. This is an example how equality search would work in a Btree index. So if you are looking for city Nagpur, earlier when there was no index, we were doing a sequential scan. Now what, if we decide to use an index scan for this, what will happen is, from meta page you will come and basically look up this root page to see which path of the tree or which branch of the tree you should follow. Now since Nagpur is, is greater than Lucknow, we decide to follow the second branch. And within the second branch, since again, Nagpur basically is between Lucknow and Surat, we would follow the first branch to get to the actual leaf node. And then within leaf node, you would do a sort of binary search to find the actual heap tuple. The other good thing about Btree indexes is that they help you in range queries. So if you are looking for all cities which are greater than or equals to Jaipur and less than or equals to Nagpur, and because of those previous and next pointers that we have, by which we have linked all the leaf pages, once you hit Jaipur, to fetch all the remaining values, you don't need to go back to the start of the heap, start of the index. You can just walk through the chain of leaf nodes and keep collecting all the rows that are still in the range that you are scanning for. Any questions here? All good? So yeah, I mean Btree is the default index type. It's pretty useful for queries where, for equality queries where you are saying, some key equals to k. It is pretty useful for range queries. It is also very useful for, queries, prefix matching like queries, where because, since the index tuples are sorted that way, you can, for example, do like am, percentage. So it will find all the index tuples which starts with am and basically collect all those rows. And as you rightly said, if there are order by clauses, Btree indexes are quite useful for serving those queries. Yeah.
Hello. Can you use the mic, please?
You mentioned you run and explain, you actually show the plan in terms of the optimizers decided that this is the search path which I should be following to get the data. But sometimes when I'm not clear in terms of what are the other options available, is there an option in PostGIS where I can see the available plans that were being worked on and this plan got decided as the one with the shortest route?
Yeah, basically, planner is smart. So what you can do is there are different GUCs to turn off, plans. Like you can say enable sequential scan equals to off. So it will sort of disregard. I mean, it try to not use sequential scan. If there is no option, it will still use sequential scan. But you will end up seeing that, if you don't use sequential scan, at least the planner's cost would be more. Now, we do that sometime, planner might think that it's not the right way, but if you actually run the query, it will run quicker than what planner thinks. That happens, and it's useful to basically try with these different GUCs at times. We don't have, I think there is a extension where you can, if you're looking for something like Oracle hints where you can force particular plan on planner.
Forcing a plan, but I remember Sybase has something called as DBCC trace on, wherein you can actually see when it made a decision, what exactly was the reason it made the decision on. So that.
I think there is way, but I don't know whether how friendly it is. I mean, I think there are ways you can print debug information, right? Collect more verbose information, but that's going to be sort of it will print a lot of internal structures which you'll have to look at. So those, what we talked about was pure Btree indexes. What if you are looking for, instead of simple queries where you are saying column equals to some value, now you want to look for, because your table might have a mix case values for city names. Somebody has, written Nagpur in caps letter, someone has written in lower letter. How do you find that information? So one way is, you do lower city equals to, in lowercase Nagpur, so that all values are, converted into lowercase and then search. But as soon as you do that, we have reverted back to a sequential scan. Again, because planner doesn't know anything about lowercase Nagpur. It knows about Nagpur written in a particular way. So that's when the expression indexes are sort of useful. So what you can do is, instead of building an index on column city, you can build an index on expression on column city. So what I do is I drop the original index and I recreate the index, but this time if you see, I have used a expression there. So so when this is done, every time a row is indexed, instead of using the actual value stored in the tuple, we first apply the expression, and whatever is the resultant value, that value is stored in the index. So in this case, even though the heap tuple might have Nagpur written in all caps, the index will have it all written in lowercase. So later when you do a query like this, because index or the planner knows that the index is actually using same expression that the where clause is using, it can suddenly now find that index useful and take that path. Obviously, we are again doing bitmap index scan for the reasons that we discussed, which is like there are too many duplicates there. So expression indexes, you can use arbitrary expressions, user defined functions, but what Postgres wants you to have all those functions and expressions to be immutable. If you know that a function is modifying database state, and if you still mark that as immutable, planner would be happy to pick that index, but be ready for surprises in your database in that case. Also, the where clause should use the same expression that has been used in the while defining the index for it to make use of that expression index. What if you don't want to index all rows in a table? For example, let's say there are 25 different cities, but what you care about are just 4 metro cities, because that's where my queries are going to come from. So instead of indexing every row in the table, you have a choice of indexing subset of rows, and the way to do that is to use partial indexes. When you do partial indexing, what you do is you stick a where clause to your create index definition, and by that you are sort of telling when you are building the index, you are telling the engine to skip certain rows. Those rows would never appear in the index. Because you index a lot less rows, obviously your index would be shallower, which would speed up your select speeds. Also, because you are not indexing everything, your inserts and updates overhead would be smaller, because you don't have to go to the index every time when you do an insert to the table. This is an example how you again sort of build a partial index. What we are doing is we are saying create index, city index, but only on rows which are matching these 4 values, any of these 4 values basically. So then if you run a query where it says city equals to Nagpur, it's not going to use index, because there is these rows are not indexed at all. So planner knows that based on its stats that most likely this particular column value is not indexed, so let's not use it. Whereas if you look for city equals to Mumbai, it will actually use index scan. Also, there are no bitmap scans this time, because there are lot less duplicates there. Okay, the next thing is what we call index-only scans. This got introduced in pretty recent releases of Postgres. With index-only scans, what we are trying to do and achieve is, if there is enough information available in the index itself, never go to the heap. And as you would imagine, that can be awesome at times, right? I mean, if you don't have to go through the heap, which is randomly ordered, scattered everywhere, your queries would be really cheap. But for index-only scans to be used, there are at least two conditions that need to be satisfied. One is, as I said, your query, as you said, as you would probably see, I'm not doing select star this time. I'm selecting a specific column on which I know there is an index. So that helps in index-only scans. The other is, the planner needs to know that the visibility information is sufficiently updated for many of the pages in the table. Now again, I'm not going to get into details there, but what typically that requires is a periodic vacuum on your table so that visibility maps are all updated. Those two things can actually improve you to speed up index scans. Okay, so that's about all about Btree indexes. Next, I want to basically talk a little bit about BRIN indexes. These are BRIN stands for Block Range Index, which got introduced pretty recently. Yeah, I think that's a question.
I have a question regarding partial indexing.
Yeah.
So if I have Nagpur and Mumbai in the where condition, will it use that index?
Nagpur and, or you mean or, because and doesn't make, so
yeah, I mean,
or, yeah, it will still use that,
okay,
that index.
And in that case, is it better to have partial indexes, more partial indexes, or just one index, one complete index? Like I create multiple partial indexes.
Well, I think most likely it will depend on how many rows you think would get filtered out, and it's pretty hard to say give one concrete answer there, but it would depend how many rows would partial index skip, thus reducing the overhead for selects and inserts. But at the same time, how often you query for rows which are not indexed, because as soon as you query a row which is not indexed, the only thing that it can do is a sequential scan, right? There is no point having two indexes where you also have a partial index and a full index, because then the cost is.
I'm saying if I make partial indexes that covers all the rows.
Well, that doesn't make sense, right? Because then it's no longer a partial index. Basically, if it's covering all rows, why even have that predicate attached to it?
Yeah.
Right.
Yeah.
Yeah, depending on what values you have passed there. In is nothing but basically a set of ORs, right? So it will. So yeah, the next type is BRIN index. These were introduced in 9.5, and there are very specific use cases that are catered, but catered very well by BRIN indexes. BRIN indexes are useful when you know that the data in the heap is more or less sorted. It need not be like really sorted, but let's say you basically cluster your table pretty often on some column, so you know that my heap is generally sorted. Also, the table is really, really large. It's like multi-terabyte data, and if you try to build an index on a table which is like 100 terabyte, the index itself might be 20 terabyte large, right? And you don't want to do that. So what instead you can do is you can build a BRIN index, which instead of storing every information or information about every tuple in the heap, it sort of stores a summary information about a range of blocks. It could be one block, or it could be 10 blocks, 100 blocks, depending on how large the table is, what sort of parameters you have defined. But it will store summary information, and by summary I mean it stores the min and max value in the given range of blocks. So between, say, I think I have examples, but since it doesn't store all index, all heap tuples, it doesn't index all heap tuples. the scans using Brin indexes are always lossy scans. They'll always resort to bitmap scans. There is no vacuum overhead here because since there are no direct pointers from the Brin index to the heap, whenever you vacuum your underlying table, the index is not touched at all. I'm sorry if those words are not readable, but what I'm trying to show here is you got a heap of 4 blocks, blocks 0 to 3, and then in every heap there are set of tuples. The first block contains Madurai, Agra, Coimbatore till Vadodara. Now the data within that block is not sorted, right, and it has sort of mix of data. But what we know is the minimum value in that block is Agra and the maximum value is Vadodara. And similarly, we can find information about every block. So what we do is in Brin index, we store that block 0 contains tuples within this particular range. We don't know what values are there, but we know that there is nothing which is lower than Agra and which is nothing which is more than Vadodara. And we do it for every block. So as you would imagine, this index is going to be pretty small, right? Because it's not indexing every tuple, it's just putting some summary information. But when you do query, like for example, when you are looking for city Vadodara, it can skip block and 2 completely, 2 and 3, sorry, because it knows blocks 2 and 3, they do not contain any tuple which is, which could be Vadodara. But it cannot skip blocks 0 and 1 because Vadodara fits into both these ranges. So it must scan block 0 and 1, but it can scan block 2 and 3 completely. That's how the obviously selects are slightly expensive, or actually more expensive, because now you need to scan multiple blocks, but the index size is pretty small. The footprint is pretty small. A good way to use Brin indexes is to make sure that your heap is as sorted as possible. So if now in this case I have sorted the heap completely, and then if you build a Brin index on top of that, when you are looking for city Jaipur, for example, you can skip block 0, 2 and 3 completely and just go to that block number 1 and look for all tuples in that particular block. So that way, Brin indexes are very useful when we are dealing with very, very, very large tables. 2 other types of indexes that I want to very briefly talk about is, one is called GIN index. GIN stands for Generalized Inverted Index. In this index, what we do is, instead of store, the characteristic of this index is that a particular heap tuple might be indexed by multiple index tuples. And this is pretty useful. For example, let's say you are indexing a English Word document, right? And later on you want to search for keywords. So how do you quickly find out what all documents actually contain word Postgres? So what GIN offers you is, you can store one index tuple where you say my key is Postgres, and this is the list of tuples in which this word appears. So anytime when you want to do a query for a key, you can quickly find the list of tuples and go and fetch those tuples. So this is pretty useful for storing when there are too many duplicates for a indexed value. As I said, this is pretty useful for looking up indexes, and if some of the built-in modules like PG diagram, which is used for similarity search in Postgres, they typically use GIN indexes. Hash indexes, these were improved quite a lot in recently in PG10, because they are now both crash safe as well as they can be replicated correctly. Earlier, hash indexes were supported in Postgres for quite a long time, but because they were not crash safe, I think hardly anyone used them. hash indexes can be much smaller than Btree indexes because instead of actually storing the index value, you just store the hash of that particular value. The negative side of hash indexes is that they cannot be used for range queries because anybody who is aware of how hash tables are maintained, there is no ordering within the hash table. You can quickly find a particular value from the hash table, but you can't find a range of values from the hash table. As you would see, for the same, so what I've tried to do is build a Btree index and a hash index on the same column. As you would notice that the hash index is much smaller as compared to the Btree index. The last type that I want to touch upon is generalized search trees. These are special types of indexes that are supported in Postgres, and I think a lot of systems actually use them. Now these are generalized search trees, so there is no a particular characteristic of, there is no ordering within the tree or nothing of that sort. It basically sort of satisfies some minimum properties, and that can be exploited to build pretty interesting indexes. Like PostGIS use it pretty often, or if you want to build an index on a point data type where you want to quickly find what are the 10 nearest point to this particular geographical location, or you want to sort of find a bounding box which includes all the geographical locations you want to look for. GIST is pretty useful and very extensively used for those kind of data types. Probably not enough time to get into any of those details. These are also called generalized because Postgres offers you a sort of extensible mechanism by which you can create your own search trees using GIST. They are used for, as I said, GIS queries, nearest neighbor queries. These are all sort of served by, these are multi-dimensional queries which a Btree or a hash tree or a BRIN would never be able to support. GIST is the way to sort of go there. I think I might be running out of time, so I'm going to quickly go through the last couple of slides. How do you find basically whether I'm missing an index, or I'm sure this might have been covered by other talks, but one good way is to look for PGStats, use PGStat statements or auto explain, where you can collect this information, analyze the information, or look for this into the stats that are maintained by Postgres. So Postgres is pretty is heavily collecting different stats from the system, and it's a good idea to look into those stats periodically to look, see for any improvements. And as I said, sequential scans are not always bad, so don't try to force an index scan all the time. Maybe sequential scan is the right thing to do. How do you find a missing index? Okay, I'm basically I ran a pgbench query, and I got a very low TPS, which is like 3 transactions per second. My laptop can consistently do much better than that. So something is wrong. I don't know what. So what I do is I start looking at the stats, and what I notice is suddenly the pgbench account state table, which is the largest table in the benchmark, is actually doing too many sequential reads. So that sort of triggers me to look into what's going on. The other 2 tables, they also are doing sequential reads, but that's sort of understandable because those are pretty small tables. So I know that's fine. There is nothing wrong if sequential scan is used. But accounts looks bad, and oh, I think I found the culprit. What I probably accidentally did was dropped the primary key on that particular table. Obviously no one does that, but for the sake of it. So once I basically see that, and then I understand, okay, there is no index on this particular column that is queried very frequently by the benchmark. So I'll go ahead and add re-add the primary key on that particular table, and from 3 transactions per second, now I can do 733 transactions per second. Just like missing indexes, I think unused indexes are also bad, I think, and you should look for them in your system all the time, because if nothing else, they take space, storage space, and more importantly, you need to manage, the engine needs to maintain them. So for every insert, update, delete in the table, those unused indexes are still maintained. Vacuum becomes, slower, because vacuum has to again make sure that all the dangling pointers from the indexes are removed. So it's quite important to look for unused indexes and remove them. One way to sort of look for them is you can look at this PGStat user indexes system view, where it will show you that this particular index, which I redundantly built on the accounts table, has done 0 index scan, which is sort of a trigger point to you to look further. And maybe you should investigate if you really need this index, because nobody is using it. The only, I think, point to keep in mind, and we tend to forget this, if you have a a hot standby system, sometimes what happens is your primary is not using an index, but your hot standby might be using it. So just because your primary is not doing any index scans, that doesn't mean that your hot standby might not be doing it. So make sure that you look at both places before dropping an index. So that's a quick summary. Btree is pretty useful for equality and range queries. Hash indexes, if you only do equality queries, it's worth looking at. Brin indexes, very large tables, if they are clustered, if the heap is clustered, that's even better. Gen, when you have a column with multiple, many duplicates, or if you want to, index multiple keys from the same tuple, Gen is the index to look for. And everything else, I think, just PostGIS, bounding box, nearest neighbors, all these queries can be addressed by GIST quite nicely. Always look for, as I said, look for slow queries, look for indexes which might be missing, or indexes which are rather unused, and try to clean your schema accordingly. And look, index only scans are pretty useful, so look for periodic vacuum on your database. I think that's about it. I hope I finished in time. So
Thanks,
thank you so much.
You can take a couple of questions.
Okay.
Is that Brin Index, is it not a good fit for time series data?
It actually could be a good fit for time series data if you are basically in.
Because we'll have loads of data, and everything is sequential.
Right. If you are, it's a append only table, where you dump the time series data. I think Brin Index is useful for that kind of workload.
Can we get a really good performance? What sort you can expect? If we go with Brin Index.
It's pretty difficult to answer that, but I think it's what I can tell is it's worth considering, definitely.
We can try and see.
Yeah.
Okay, fine. Thank you.
I think that's it.
Well, these are typically determined by your configuration parameters. Like we have a parameter called random page cost, sequential page cost. So depending on how the default values are, sequential is 1 and random is 4. So random is typically considered 4 times slower than sequential. I think the planner makes its call based on a lot more information, right? What kind of where calls you have added to the query, what is the selectivity of those particular columns, what is its estimate about how many rows it's going to return, and based on this it will calculate the aggregate cost of doing sequential scan or an index scan.
Thanks, Pavan. I think if you guys have any question, you can catch up with Pavan offline.
We can catch offline. Yeah. Thank you. Thank you all.
Thanks.